Well, hello everyone. Let's talk about electric current, resistance, and Ohm's law. That sounds like fun to me. Okay, so we're going to talk about current, introduce that topic, concept. That leads us to Ohm's law, which is what happens when you add resistance to current and you reduce the ability of the current to flow. And then we'll talk about resistance and resistivity, how you can calculate how much resistance a resistor will provide you. And then we'll talk about electric power and energy. So, starting with current, your calculator, bloop, numbers come up, nerve impulses carrying signals from your eye to your brain, ultrasound device sending a signal to a monitor, for example, to see a baby or something. All of these involve the movement of charge, or what is known as electric current. Okay, so movement of charge is electric current. Electric current is defined as the rate at which charge flows. It's the change in charge, which has the unit coulomb, over the change in time. How much charge moves in a certain amount of time. If you can push a ton of charge over a short time, that's a high current. The direction of current flow is always from the positive to the negative. It's in the direction, like when we draw electric field lines, it's in the same direction from plus to minus. If you recall a parallel plate capacitor, we've got a positive potential and a negative potential. If you drop a positive charge in there, plus, it's going to feel a force, which is going to be of the strength Q times E. So if they ask you how much force will this charge experience, well, you have to calculate the electric field, which will be V1 minus V2, V1 minus V2 divided by this separation D. Once you figure out what that is, that's the electric field. You can take that and then take this charge times that electric field strength, and that'll tell you how much force is on it. Then you can say F equals ma. If you know the mass of the particle, you can actually calculate how much it accelerates, which is kind of cool. But all you need to care about here is that when you have a positive potential and a negative potential, the electric field lines exert a force on a positive charge in the direction of the negative charge, okay? That's the main thing. All right, so let's say you've got a battery with a positive terminal and a negative terminal, and you want to light a light bulb up. So this light bulb has a metal screw part here, and then there's this black insulator, and then at the bottom there's like a silver dot, which is the other connection. And so current needs to be hooked to this part so it can flow up through the filament and then back out isolated out the bottom to the other side. So if we start trying to hook up our circuit here, a simple circuit, we want to go from the plus side onto the light bulb, force the current through the light bulb, and then out the bottom and back to the battery. We don't want to short circuit it so that the current just flows this way. We want to force it through the filament, and that's what causes it to light up. Congratulations, we just made our first circuit. This is pretty exciting. What is causing the light bulb to glow here? That's the electric current flowing through a resistive element. The element heats up, and that heat glows when it gets hot. Okay, so what is current flow? What is current flow? Current flow is the motion of charges. It's in the direction of positive flow. So these positive charges, we imagine them flowing this way. That's the direction of current from the plus side of a terminal through the negative side of a terminal. If you want to quantify charge, how much current is there, how much charge is there, that's change in charge divided by change in time. The unit of current is the amp, and that's coulombs per second. That's the unit of it. So the unit is amps, so we write it with an A, okay, after ampere. Who was a dude? Okay, so current, coulombs per second, amps. So sometimes you'll be given problems that'll say there's 4 amps of current in the circuit, and you'll know that that's 4 coulombs per second, okay? That's what 4 amps means, okay? So sometimes you'll have to calculate current from coulombs per time, sometimes you'll have to calculate coulombs from amps, and so on. So you'll play around with those equations. Now, one thing you have to get used to is our make-believe schematics. So this is in real life. What you have is you have a car battery, for example, literally hooked into your headlight. We represent lights as resistors in circuits, and resistors in circuits are represented by this weird squiggle, okay? So that's our resistive load, as we call it, resistive load, and that's a light bulb, and we draw batteries with 2 lines like that, where the longer side is the plus side and the shorter side is the negative side. So then we know that the circuit, the current is going to flow around, in this case clockwise, from the plus side to the negative side, okay? And so this is called a schematic, okay? Schematic, okay? Automatic schematic. There we go. So current is defined to move in the direction of the electric field. Remember, the electric field is what forces the charges to move, and positive charges move in the same direction as the electric field. So if you have an electric field move with a vector pointing in that way, then the positive charges are going to feel force in that way because they go from plus to minus, and so that's just something you have to learn and commit sort of to memory. When we talk about current flow, we're imagining the positive charges are the things that are moving, okay? Even though the electrons will be going in the opposite direction, the positive charges will be moving in the same direction as the current. Okay, now there's an interesting thing called drift velocity. Drift velocity is, it's a little bit weird, but basically when you turn a light switch on, the lights turn on pretty much instantly. So you complete the circuit where your hand is, and somehow the lights immediately respond. So the effect of electricity is almost instant. That is almost near the speed of light that your current flows. But interestingly, the actual charge carriers, the electrons, the protons, and so on, they actually travel very, very, very slowly. Okay, so the charges themselves don't move very much. But when you flip it on, they just bump into each other and send a signal down the line. So 10 to the 8th meters per second is about how quick a current will flow in terms of the signal that gets communicated, but the charges themselves travel significantly slower than that, on the average of 10 to the minus 4 meters per second. That's a huge difference. This average velocity here of the actual charge carriers in the circuit, in the wire, that's the average velocity of the charges. That's called the drift velocity. So that's when you turn on current, the electrons kind of go slowly, but their signals get propagated a lot more quickly. So what happens is an electron, when you complete the circuit, this electron comes racing in, boom, bumps into all these, and they all respond, but they don't move. They just send the signal of them getting hit into the other ones, and then at the end, those very last electrons feel a kick too. You can think of it like this. This is a slinky here, and you can see the pulse. Even though the coil doesn't actually move, the pulse, boop, boop, there we go, let me turn this on, boop, boop, that pulse travels a lot faster than the individual slinky parts, okay? And so this shock wave of electric, it's like an electric field shock wave basically traveling through, which causes the current, okay? So drift velocity, right? The electron is going to be banging into stuff as it tries to move in the direction of the force that it's experiencing, and which is opposing the current and opposing the electric field. So remember, electric field goes from positive to negative, and the electrons flow from minus to positive. So the electrons will be moving in the opposite direction of the current and the electric field, but your drift velocity will be opposite the electric field and current, because that's where the electrons are going to be moving around. Like in a conductor, in a metal, it's the electrons that do most of the moving. Okay, so we have another equation which is a little weird, and we want to calculate the drift velocity. So what does drift velocity depends on? It depends on the number of electrons you have in a cross-section of the wire, which we call the density. And then those electrons are going to move through a volume. So that you've got this many electrons in this area, and then that area is going to move over a certain amount of time. Okay? The distance that it travels, x, the distance that this chunk of electrons travels, can be written as rate times time, where the rate is what we want, and that's the velocity, the drift velocity. So if we can figure out this distance and that time, we can figure out the drift velocity. Okay? So let's start by trying to quantify all this. So the area of, let's say, a wire that's a circle is pi r squared. That's the cross-sectional area, it's this pink area. The charge density, n, is the number of charges in that area. And the total current, then, is going to depend on the total amount of charge. What's the total amount of charge? It's the number of charges per area times the area times the distance. Okay, what is that telling you? It's saying take the number density, multiply by this area, and then multiply that area by this distance, x, and that's going to tell you how many electrons are in that area, and then we want to say over this amount of time. So how long did it take to move this number of electrons through that area? That's what we're trying to calculate. So we go from total charge, total time, same thing, our total current, and then we multiply the whole thing by Q because that's the charge of any one electron. Now we replace x with our drift velocity times time, and you see that the times cancel out, and so we have this nice equation which is just nqa times the drift velocity. So what is that? That's the charge density, which is basically the number of electrons in your material per area, times the charge of any one of them, times the area of our wire, times the drift velocity. So how is this useful? We can rewrite that equation and solve for the drift velocity. So if we can, now this A is area, keep in mind, but we can know if we have 2 amps of current, 4 amps of current, or whatever, we can calculate the drift velocity of the electrons in a wire by measuring the current we're pushing through it, and then dividing by the charge density, which is a property of the material. We can just calculate what that is or look it up, times the charge times the area. So this is a very simple equation, and it just says if you have an area, a wire with a certain size, cross-sectional area, and you know how much current you're pushing through it, and you know the property of the material, n, then you can calculate the drift velocity of the electrons flowing in the thing. Okay, that's a weird thing to do, I agree. Why would people do this? But it's fun, so, you know, calculate the drift velocity of a current in a wire. So we've got an example here. It says calculate the drift velocity of electrons in a 12-gauge copper wire. So if you do any electrical work or become an electrician or something like that, or do any sort of work anywhere, the gauge is the thickness of the wire, and the gauge determines how much current can flow in the circuit before the wires heat up and melt. So you've probably heard that you shouldn't plug a space heater into a power strip or a extension cord, and most of the time it's because those extension cords are not designed to handle that amount of current over that distance, and so you have to make sure you're not overloading the wire. So anyway, 12 gauge, what does that mean? It's literally the thickness of the wire, and according to this, it's 2 millimeters thick is what a 12 gauge wire is. So you've got a 12 gauge wire carrying 20 amps. Given that there is 1 free electron per copper atom, calculate the drift velocity. Okay, so we know that there's 1 electron per copper atom, so we can figure out the density of electrons in copper by looking up the density of copper, basically. And so that's here, and we can figure out how many electrons are in that then. And then all we need to do is we've got a wire with an area, cross-sectional area, we've got the diameter of it, we're going to divide by 2 to get the radius, do pi r squared, that's going to be the area. We're pushing 20 amps through it, and so we've got 20 amps, we've got our area, pi r squared, we've got the charge of an electron, Q. All we have to worry about now is the number density, n. Once we have the number density, then we're golden. So we look through this, the strategy then. We want to calculate the drift velocity using this equation, solve for the drift velocity. We know the current, we know Q, we know the area of pi r squared, we know the density of copper. What we need to do now is take the density of copper and convert that into the number of copper atoms. Okay, so we know that there's 8.8 times 10 to the 3 kilograms per meter cubed, but what we want to do is convert that into how many copper atoms are there then. So that we have 63.54 grams for every mole of copper, and then we have to convert from mole to atoms, to the raw number of atoms, and there's 6.02 times 10 to the 3 atoms for every mole. So we're going to take this, we're going to convert to moles from this, and then we're going to convert from moles to atoms. Once we have atoms, that's literally the number of copper atoms per volume or whatever, we can just plug that in. And so we get 8.3 times 10 to the 28 electrons per meter cubed. That's our number density, that's N. And our area is this, and we get meters squared because that's what area is. So we solve for our drift velocity, plugging all these things in, and we get negative 4.54 times 10 to the minus 4 meters per second. So that's it. That's how you do that. That seems a little weird. Spend a little time on that just to get comfortable with it, but it's pretty straightforward. Okay, so Ohm's Law. Ohm's Law, resistance in simple circuits. When you hook a voltage to a conductor, it applies a potential voltage V. This creates an electric field, and the electric field exerts forces on the charges, and that's what causes the current to flow, is this electric field pushing charges around. Current is I'll then have to reboot. Current is proportional to the voltage applied. If voltage drives current, what impedes it? Okay, so the more voltage we apply to something, the more current we can get, but why don't we just instantly get all the current? What stops it? Current has a maximum flow rate for a given voltage. It's basically limited by the material that the wire is made out of and the number of electrons that can move and how quickly they can move and what sort of barriers they have to jump around. This limit is caused by the inherent resistance of a wire, and it limits the rate of current. You can also make artificial resistors, so you've got a nice wire coming in here, and then you make, this is basically like American Ninja Warrior or something like that. The electrons have to go through an obstacle course to get from this side to that side, and it slows them down. It takes a while to do that. They got to figure it out, work out a little bit, and so on. But these are all different types of resistors, ones that you see in a typical circuit. This one has a heat sink on it, aluminum, to help dissipate some of the heat. Looks like it gets pretty hot. This is a 0603 surface mount resistor. It looks big on the picture, but that one you probably wouldn't be able to see. They're really small. I mean, you'd be able to see it, but you wouldn't be able to read 0603 on it, maybe. I mean, I could because I have amazing eyes. Okay, so Ohm's Law, V equals IR. This is the relationship. The more voltage you pump into a circuit, the more current you get. And it's proportional to the resistance in the circuit. Okay, the resistance is the thing that's stopping it. Resistance is measured in ohmegas, which we call ohms after a guy named Ohm. Okay, so volts equals current, or amps, times ohms. And that's your, or resistance is volts per amp. So you can think of it that way. V over A is equal to ohm. Okay, ohm. So this is what a battery looks like in real life, a 9-volt battery, and you would hook it up into 2 of these resistors, or 1, and then schematically in our fantasy land, this is how you would draw that. So our battery, again, the plus side is the longer leg of this thing. Current flows from the positive side to the negative side, and then we've got a resistor in here, or in the case of the picture, we would actually have 2 resistors if we wanted to match the 2 resistors we see here. But these 2 resistors are in series, so we could just add them up in series to get 1 resistor, which is something you will be comfortable doing. But if you want to calculate the current in this circuit, it's literally V equals I times R. So you can just take your voltage, 9 volts, divided by your resistance. In this case, it would be a total resistance. R total is equal to R1 plus R2. So we would have a total resistance here of 9,000 ohms because we're measuring kilo ohms. This is kilo ohms or 1,000 ohms. Okay, so notice we're not talking about this yet, but our total in series is R1 plus R2. That is different from capacitors. If you remember capacitors in series, instead of being, so this is resistors in series. Capacitors in series add like the inverse C1 plus 1 over C2. Okay, so just remember that. The capacitor and the resistor are complete opposites. When we talk about that in a little bit, next chapters or so, you'll have to deal with that at that time. Anything in my teeth? Okay. So you can measure the voltage across a resistor by hooking a voltmeter to it. Okay, and a voltmeter, this voltmeter is hooked, as we would say, across the resistor or in parallel with the resistor. It's not in series with the resistor, it's in parallel because the connection is across the resistor and it allows the current to flow in both directions. So if the current can split, then you're in parallel. If the current can't split, then you're in series. And the key here, and we're going to build on this concept, the total voltage in this, let's say this is an 18-volt battery, then the voltage drop across this resistor is also 18 volts, and it's equal to the current and the resistance in that circuit. Okay, this is really important because if I go back to this picture, we've got a 9-volt battery. The voltage drop from here to there is 9 volts, but this is going to be 4 volts and this is going to be 5 volts, and that is going to add up to your total circuit. Now, it's probably not exactly 4 and 5 volts, but the point is the drops, every time you go through one resistor, you drop a little bit in potential until you go down the entire amount from 9 volts to 0. So you always start at 9 volts on the battery and you always end at 0 volts, and you drop at every circuit component along the way. And we're going to talk more about that, so if that's a little foggy, don't worry about it, because we're going to talk about that when we get into actual circuits. Okay, so far all you care about is that V equals IR. All right, and that's what we're calculating. So what about R? What if you want to calculate the resistance of a resistor? Let's say I give you the resistance and you can calculate the current or the voltage, but now you want to say, well, how do you calculate the resistance? This is based on the resistivity of the material. So the resistance a resistor has depends on two things: what it's made out of, its material, and how much of it there is. How long is that resistor? How fat is it? How big is it? So it depends on the area, the size, and the length, but it also depends on the material itself, which we encapsulate in this new term, resistivity, which is the Greek letter rho. Okay, very easy. If you want to calculate the total resistance of something, it's just its length divided by its area times the material property resistivity. That's it. That's the whole thing. So you physically measure the size of your resistor, and that's how you do it. And then the resistivities for certain elements here, there's a giant table in this book. I've only given you a piece of it. Ton of materials and all their resistivities. And you can see that some things have very low resistivities, which are conductors, and then you've got some insulators which have very, very high resistivities. Okay, so you can run the gamut. So before I move on to that, there's an example here. It says a car filament is made out of tungsten, which has a resistance of 0.35 ohms. If the filament is a cylinder this long, what is its diameter? Okay, so we want to figure out the area so that we can figure out the radius, then we can multiply by 2 to get the diameter. In order to solve for the area, we have to rearrange our equation to be rho L over R. We know that it's 0.35 ohms. We know that the resistivity of tungsten, according to our table, is 5.6 times 10 to the minus 8 ohm meters. And they told us that the filament is 4 centimeters long, so we plug that in for the length. And then we solve for the area, which is 6.4 times 10 to the minus 9 meters squared. We know that the area is pi r squared, or pi d squared over 4 if we replace r with half d. And then we can solve for the diameter. That gives us 9 times 10 to the minus 5th meters. Okay, so that's small. So that's how you calculate the resistivity, the resistance of something based on its resistivity. All right, so now the temperature variation of resistivity, you'll notice in that question it says it has a cold resistance of 0.350 ohms. That's because as things heat up, their resistance changes, and sometimes it gets easier to push current through it. Sometimes, so the resistivity goes down, sometimes it goes up. It just depends on, you know, if you think about it, the hotter something gets, the faster the elements are moving around, and the harder it is to, you just bump into more things all the time. Okay, so in this case, the equation, the resistivity is the property that determines resistance, and that resistivity changes, it's a function of temperature. Okay, so as things heat up, you can see this this critical point when it goes from superconducting to non-superconducting. So superconducting is when your resistance is basically zero, and then as things heat up, then kicks on, and then you're no longer superconducting. So anyway, this resistivity value is temperature dependent. Most of the time you don't have to worry about that because we'll be considering things either the cold temperature or at room temperature or something where we just we already know what that is. But this is just one more thing to make you learn. And the resistivity changes with temperature, and it depends on this other value, alpha, which is just a coefficient you can measure. All of these things, rho and alpha, are experimentally determined things, quantities. Okay, just the resistivity and the resistance go together, since the equation for resistance is directly proportional to rho. You can just replace rho and r here. And that's how these thermometers work, is they measure resistance of the current flowing through a resistor over time, and then as temperature changes, the resistance changes, which means V equals IR, which means the current changes. You've got a voltage in there of a battery of like 3 volts or whatever, so that's constant. So if your resistivity changes, your current changes, and if you have a current measurement, then that's all you need to measure temperature. Okay, so electric power and electric energy. Electric energy is eventually converted into heat by a resistor, or into work by an electric motor. Power is just the amount of potential energy you use over a given amount of time, and the energy in an electric field is Q times V, and then you divide it by how quickly you're doing that is your power. Okay, so if you look at this equation, Q over T, we're going to do this a lot in these chapters, is replace Q over T with current I, and that's what we're doing here. So this is your new equation, PIV, P equals IV, and that's the power that a circuit consumes, and it's current times voltage. The unit is the watt, and the watt is joules per second. So V equals IR, you can, V equals IR, okay, you can replace this V with IR and you get I squared R, or you could replace I with V over R and you get V squared over R. So these are the kind of common equations you're going to see relating the current and voltage and resistance in a circuit to the power that it consumes. So P equals IV, power equals current times voltage, it equals V squared over R, and it equals I squared R. So those are the three equations you're going to use all the time. I'm going to ask you, oh, I've got a 9-volt battery using 1 amp of current. Oh, that's 9 watts. Okay, I've got a 9-volt battery with a 2 ohm resistor in the circuit. What's the power consumed by the resistor? 9 squared, 81 over 2 would be the power consumed by that. Or I've got a 3 amp circuit with a 40 ohm resistor. What's my power consumption in that circuit? I squared 3 amps times 4 ohms. Okay, so you're going to be doing that all the time. Now, one of the things is you could have a battery like this with the plus and the minus, and then you can have 1 resistor and 2 resistors. Okay, now this equation and all these equations can be used for either IR here or IR here, or imagining this as one circuit and having just one IR. So this will be I1 R1 and I2 R2, and in this case, the current in a circuit is, oh no, I can't erase. The current in a circuit is constant when it's in series like this, so you're going to have a different resistor value. You'll have a different V1 there, V2 there. Everything will add up. Okay, I'm confusing you because this is not what we're covering right now. But the point is, you can use these same equations for individual components or the entire circuit as a whole. Okay, and we'll talk about that later, so just ignore everything I just said if it was confusing. I'm sorry. I hate when I do that. All right. The cost of electricity. So let's say you want to optimize your house or determine whether or not solar makes sense or how long it'll take you to pay back the cost of buying a solar system so you don't have to use electricity from the grid. The total amount of energy that you're going to use is the power, the wattage, times the time. So this is commonly seen as the kilowatt hour. That's the unit on your energy bill, for example. And it's how many watts of energy you used over a month, and it's measured as kilowatt hours. If I go to this, we've got this example here. So kilowatt hours is the main unit, and there's an example here that you can go through. If the cost of electricity in your area is 12 cents per kilowatt hour, what is the total cost of using a 60-watt bulb for 1,000 hours if the bulb is 25 cents? If we replace this bulb with a CFL, a compact fluorescent light, which provides the same light output but with 1/4 of the wattage, and the bulb costs $1.50 but lasts 10 times longer, what will that total cost be? Okay, so both of these things, you've got a 60-watt bulb for 1,000 hours, and it'll cost you $7.20. And then the other case is that instead of using 60 watts, it uses 15 watts, and then you get that it will be 1/4 of the cost, which is $1.80, and then it lasts 10 times longer. So the total cost over 1,000 hours, you have to divide it by 10, is 15 cents. Okay, there we go. And delete all this. Okay, so go through that example and then do it at home. Calculate, try to estimate how much it costs you to make a piece of toast. Yeah, let's do that. Okay, I'll see you guys later.